Hello, everybody. I'm very excited to be here and explain to you Paragon Genomics, who we are, and how we can help you with your research. Hopefully, everybody got lunch if they'd like it. It's right over there, obviously, if you haven't seen it. Oh, gotta turn it on. So, a little bit about who we are. Paragon Genomics was founded in 2015, headquartered right in the San Francisco Bay Area. A few years later, we launched our CleanPlex technology, which is really at the core of our technology and our kits that I'll describe here. Our kits essentially are library preparations that have really high quality design and a patented cleaning technology built into them to help researchers really advance their research in precision medicine. Our technologies are all patented and made right there in San Francisco in the East Bay. We have sales all across the United States and distributors and direct sales across the world as well. So I told you CleanPlex is at the heart of our technology, so let me explain to you what CleanPlex is. I'll give you some high-level description of it, how it works, a bit about where it can be implemented into our kits, and then we'll see some applications from our two speakers here today. So CleanPlex technology is a 3-hour library preparation. We use PCR amplification with targeted amplicons. We have a superior design method as well as a patented cleanup technology built into our kits that we say helps our customers discover more with less. So some key features of CleanPlex technology: we allow for very low input, so down to that picogram DNA input for some of our applications. We have high sensitivity and specificity, down to that 1% allele frequency detection. High multiplexing, so in just one of our panel designs, we can fit 20,000 amplicons together, as well as our samples can be multiplexed highly together, so we can do very less sequencing runs with all these amplicons and all these samples together. We're very diverse in the type of sample input we allow, the flexibility within them. So standard genomic DNA is great. We also work well with long-term storage FFPE or more degraded samples, or those rare types like cell-free DNA. We're compatible with a lot of different inputs. Finally, our workflow is simple and fast and robust. And I'll explain to you right now in the next slide how that works. In essence, it's 3 steps, 3 hours, and just 1 tube. So I'm showing the steps here. First thing is just a multiplex PCR. We take that panel I just talked to you about with all of our amplicons. You put it in a tube with your DNA and with an enzyme, multiplex PCR reaction, quick bead cleanup, and then we do our patented background cleaning, which helps remove primer dimers and cell debris, all the stuff you don't want to end up sequencing in the end. That's step 2. And then step 3, after another bead cleanup, we have our indexing PCR, where we're just simply doing another PCR reaction to add those sequencer-specific adapters onto your library. And I'm showing you different types of sequencing platforms that we have kits available for. We have many more in the pipeline this year. We'd like to say at Paragon, we're sequencer agnostic. We are very flexible for the type of sequencer that you already want to use or already are using for your applications. So after we do these 3 steps, all of our samples get pulled together and just run on the sequencer. This is just simply an image showing kind of a before and after CleanPlex cleanup technology, if you will. So in the red, you can see the different peaks and schmutz, if you will, in the background that is present. And then when you apply our CleanPlex in the blue target, dip right there, you can see that's just the library design right where we expect it to be without large peaks of unnecessary extra bits. So I have this slide here just to show you that our technology is robust, whether it's a small amplicon panel, 7 amplicons I'm showing you on the top left there, or a larger amplicon panel of 1,000 plex at the bottom right. We see nice, clean results regardless of the panel type. Here I'm just showing you a similar size 207 amplicon panel from our design compared to a competitor. And you can see ours comes into really nice uniformity, so all of our targets coming in a nice even distribution. In one of our competitors, you see a little bit more scattered distribution. In the end, this just helps you save on your sequencing, save money, time, labor, etc. So how do you get CleanPlex technology? Well, we have 20 ready-to-use kits. You just add them to your cart, purchase them, we ship them to you very fast. These are really nicely curated and tested in the field kits for very popular research topics. We also have a large array, 100 plus pre-designed panels, which are converted into ready-to-use kits upon request. Many other target types that we have curated very nice targets for in various different fields. But if you're the type of investigator who has your own custom targets that you've discovered, or you just have done your own curation, you know exactly what you want to look at, a big part of our business also is custom panel design. And this is just 4 simple steps. You just send us your targets of interest. Our bioinformatics experts plug it into their algorithms, get a great design to you, you approve it, we make it and send it to you. Turnaround time's less than a month, and we see this working great across the field. We've done over 800 designs of custom panels. You can see the different fields I'm highlighting where our panels fit into with our designs right now. And you'll hear about 2 topics today from our speakers as well. We're doing well in the literature. We're getting lots of investigators publishing work with Paragon Genomics and being pleased with the results they're seeing. And this is just highlighting some of our happy customers from great institutes like Stanford Broad Institute. We have many customers, as I said, worldwide. These are just some nice testimonials to show you that people are happy with what they've seen CleanPlex technology and Paragon do for them. And with that being said, I'll now introduce you to our 2 speakers for today. First off, we have Edwin Oh, who's going to talk about his wastewater surveillance projects using Paragon Genomics kits. He's from the University of Las Vegas, Nevada. University of Nevada, Las Vegas. And then we have Dr. Matthew Beckman, who's going to talk about his work with pharmacogenomics at GENETWORx and their custom panel they've been using to target very custom targets. So with that being said, Edwin. Oh, and this is just our Paragon community. Thank you, everybody. Thank you. And this one is you. These 2 buttons. If you don't want to, just hit the keyboard and times the bell.
And is there a mouse? Please forgive me. Can you see this mouse cursor moving? No? You can? Okay. All right. All right. Well, good afternoon, everyone. It's a real pleasure to share some of our stories with you all today. My name's Ed. I'm an associate professor at the School of Medicine in the University of Nevada, Las Vegas. I'm primarily a human geneticist. I've been spending the last 10 years or so sequencing human exomes, genomes, transcriptomes, and when COVID hit, a lot of our research, like many other people, changed, and we ended up working instead with brain sections. We started working with sewage, something that we knew very little about, and it was a real pleasure working with Paragon Genomics in interrogating SARS-CoV-2 and a whole host of other respiratory pathogens. So I always start by acknowledging the group. It's you know, this has been a team effort where we run surveillance for the state of Nevada, down in southern Nevada primarily, where there are 2.4 million people and 1 million tourists every week that come through. So being able to provide real-time information about the types of pathogens that are in the community, the types of pathogens that we might see around the strip, has been something that's been really important for the health district, and working together with engineers, public health folks, computer science individuals, and the media, it's been really key in providing information about SARS-CoV-2, variants going up and down, and also monkeypox more recently. And we're funded by a number of different agencies. So as I mentioned earlier, 2 years ago, our lab pretty much shut down what we were doing with our analyses of neurodevelopmental conditions. And so we found ourselves working together with the health district in handling hundreds of samples, running qPCR in samples. And we figured at that point that this was not really something that we could scale given what we were observing with handling of numbers. And so we asked ourselves, how could we potentially develop a system where we could analyze a whole host of pathogens, as shown here, and more recently, illicit drug analytes. And our first eureka moment came about when we started talking with a number of environmental engineers, Dan Garrity and Katarina Papp down here at the bottom left of the slide, where Dan showed me this, this really amazing piece of information in this panel here, and I'm going to walk you through this panel where in the x-axis you see time. This is March of 2020 to May of 2020, and on the right y-axis you see the number of new cases here in blue that we were observing every week, and the cumulative cases here on the left, which is really this red line here. And the interesting data for us was this black line here. We're taking wastewater from a really, really small community. We were able to observe over time an increase of SARS-CoV-2 RNA in that wastewater that was pretty much matching up to whenever we saw new cases, we saw an increase in the amount of SARS-CoV-2 in the wastewater. So we thought that this would be a great way to now expand on this pilot information and run surveillance for all the wastewater treatment plants in southern Nevada. And so this is information showing that we were able to do this, where on the left side of this slide, the main gist of this part of the slide is that here in the red, anytime we saw an increase in clinical cases, we saw an increase in the amount of SARS-CoV-2 in the wastewater. And anytime we saw a decrease, we saw a decrease in the wastewater. So this was really key information for us because it suggested not only could we detect SARS-CoV-2 as it was going up, but we could also detect it as it was coming down, which is really, really key here, right? Because we have public health folks deploying resources, vaccination teams, and they're just sitting there with hundreds and sometimes thousands of individuals waiting to figure out whether a service is required or not. So wastewater surveillance helped us know in advance that these levels were coming down. Therefore, we could figure out where these resources could be positioned better in which communities. So right here on the right is when we started asking ourselves, hey, if you can detect SARS-CoV-2 in the wastewater, we can sequence it and potentially look for variants that could match up to the sequencing information of clinical cases. And being a human geneticist, I thought that this was going to be really easy. A 30,000 nucleotide genome versus a 3 billion nucleotide genome that you and I have, this should be a piece of cake. And boy, was I wrong. Trying to sequence from wastewater was perhaps one of the most difficult experiments that we encountered, primarily because extracting nucleic acids from this really complex matrix, being able to purify it, clean it, and then sequence it, had a whole host of various molecular biology tricks that we had to introduce. But after testing a number of library prep kits to generate genomes, we met with folks from Paragon Genomics, and they were delightful in helping us compare their library prep kits to Illumina's, to QIAGEN's, to IDT's, and we found that this figure here was something that we could generate from wastewater. And what I'm showing you here is that at the top, this cartoon here is the SARS-CoV-2 genome. Here are the mutations that are typically found in this variant, the B117 variant or alpha, or the variant that was first discovered in the UK. And also down here in this cartoon is a cartoon of B.1.429 or epsilon, or the variant that was first found in California. And we would run our positive controls where we would have patient RNA, so we could find mutations as depicted here by these blue lines here that matched up to what we expected. And we could also use a synthetic genome, and then finally we would use the actual samples from the wastewater treatment plants. And what you're seeing here are the locations indicated and time. This is December 2020 all the way to February 2021. And the main part of this figure was that we could detect these variants as early as December of 2020. After comparing a number of different library prep kits, we were surprised that we could get coverage of about more than 100x sequencing reads over 90% of the genome. That was the metric that we wanted in order to compare with clinical samples. So here's sequencing of wastewater. We then compared this to sequencing of clinical cases, right? Because we wanted to match wastewater with clinical cases. Could the wastewater mirror? Could the wastewater predict? These were some of the questions that we were asking. And the bottom line here was that we only started detecting B117 right here in this blue sliver here and epsilon in January of 2021. But if you look more closely, you'll see that the sample size here is in the 200s versus 13. So chances are there were humans around during this time. It's just that we didn't have the resources to gather these samples and sequence during that time. So we've gone on to run this type of surveillance for clinical cases and wastewater, and we've been able to show that wastewater can either mirror or predict the emergence of some of these variants. But after we showed this information to public health folks, to other state epidemiologists, many of them asked, did we get lucky? Or worse, did we cheat? Did we know in advance what was going on? So earlier this year, we decided we were going to do this type of analysis side by side with the public health folks, where we would start looking at Omicron, and we would be testing real time every day for samples that were coming in. And so what we ended up doing was just representing data from each week or every 2 weeks. So this is public health surveillance, where you can see these variants here in different colors that are being displaced over time. Here's BA.1, BA.2, 212.1, and BA4 and BA5. And so this is the type of information that we can get from clinical cases over time from Las Vegas. Here's what we would see for wastewater. We would also see a similar trend for BA.1, BA.2, 212.1, and 4 and 5. So the key here is really the juxtaposition of these two data sets, and this is what we see. And so the bottom line here is that when you compare wastewater to public health surveillance, the emergence of these variants appears to be a lot sooner, where we can see BA.2 here in March compared to public health sequencing of these samples. The displacement pattern is exactly the same almost. It's just that the timing of that displacement is a lot more obvious in the wastewater. So you and I, we're going to use the bathroom today. So after we use the bathroom, if we're infected, this RNA in our fecal matter is going to head towards a wastewater treatment plant, and we're going to know whether or not there's SARS-CoV-2 coming from this part of the city. How many of us are going to go back and get tested at a public health unit? Maybe 10%, maybe 20%, That's basically why wastewater surveillance is always going to give us information a lot sooner than public health surveillance, I believe. It's something that we're testing with a number of other states to figure out whether we have that specificity and sensitivity. However, so far, it seems like we do have that. So we've set up a dashboard for the entire state, and we're running surveillance for a number of different wastewater treatment plants that covers urban areas in southern Nevada and also rural areas. There have been a number of different counties that wanted to get this type of information so as to provide an early warning system. So given that we could do this for SARS-CoV-2, we also wanted to look at other respiratory pathogens, other respiratory viral RNA and DNA that can be found in fecal matter, that can be found in urine, that can be found in any type of water that goes through the bathroom, showers, or drains. And so influenza, or viral RNA for influenza, is something that can be found in, and forgive me, I know it's lunch, but that can be found in you-know-what. So, so we wanted to work together with the public health folks to ask that question about influenza. So typically what you find during a year across the country is that influenza right here in the gray starts up in November and December. We start seeing clinical cases show up around this time. The interesting thing that happened to this country early in 2022 was that many of the states saw a surge in March and April. There are some exceptions. Florida, Rhode Island, they saw a peak in October. But for the most part, a lot of us saw this peak in March and April. So we wanted to ask that question. Could we have detected this in advance? And could we have provided an early warning system? This was more of a retrospective study that we're now turning into something that will help provide an early warning system. So we did the surveillance for elementary schools. Children, as many of you know, will bring home these types of respiratory pathogens, and we wanted to understand whether could we go from a wastewater treatment plant closer all the way to a building, a hotel, a elementary school. And as you can see here, while we were seeing clinical cases go up, we found 3 different schools that were showing positive results for this RNA. The interesting thing is this is when we start talking about Paragon Genomics, and we wanted to know, can we sequence this RNA? Can we figure out if there might be a pathogen that might be vaccine resistant? And lo and behold, we were able to sequence the genome, and here's the really, really interesting thing. This variant that we discovered through the sequencing belongs to a clade called 2A.2. And 2A.2 was actually discovered a few months before we found this, before we had this finding. And 2A.2 has been described as being vaccine resistant. So the flu vaccine was updated as a result of finding this variant. So we have proof of principle that in wastewater, we could have detected this from the get-go. We could detect it now and be able to provide information whether the flu vaccine is something that's going to work for a variant that will be circulating. Now, because we can do this for influenza, when monkeypox reared its head in July, we were running surveillance for the Strip and for bars and pubs that were around the Strip. And here's information about clinical cases that were going up primarily in August and September. This is public health surveillance. In October and November, it has dropped dramatically, but we're still detecting monkeypox in the wastewater, suggesting again that with public health surveillance, there are limitations in being able to understand transmission of an infectious disease. But with wastewater, we can always find it. And therefore, we can always deploy messaging and vaccination teams to areas where we see an increase in monkeypox RNA. And again, naturally, because we can detect it, we wanted to sequence it. We wanted to understand why was it that so many of us missed monkeypox, given that it was already circulating in this country 3 years ago. And so this is a collaboration recently with Paragon, and at this point, we still need to we still need to change a few parameters. The monkeypox genome is 200 kb versus 30 kb. Not that much bigger, but we think we have to make a few adjustments in order to improve this metric. And finally, I think the reason that we started going a lot more into this science was that wastewater genomics is something that hasn't been really done in the last couple of years, because even though wastewater testing is something that's been around for the last 40, 50 years, it's been primarily one of a binary result. Is it there? Is it not there? But with NGS and the availability of NGS more recently, I think SARS COVID-19 allowed for us to introduce this type of technologies. Us and many other groups around the world introduced this technology in looking for variants. The challenge is that many communities that do wastewater testing always say the same thing. Sequencing is expensive. How do you expect us to do it? And it's really hard. And so because what we've been doing primarily has been going down here with generating these libraries and sequencing on an Illumina platform and getting these metrics, we really want to transition to ONT, where we could be in a position where these machines, these sequencing machines, didn't have to live at wastewater treatment plants, and we could deploy a flongle and get sequencing results. This has been the biggest challenge for wastewater testing, the difficulty and the financial burden in being able to house a $300,000 machine. And here are some initial results where we're seeing coverage and depth that's matching what we were observing in the beginning when we were running a lot of these tests, and we think we can do better on the ONT. This is rapid barcoding, where we take the final library that's made here, we clean up that final library, and we index. It's a 5-minute step, and then we sequence on the flongle. And we can get decent results right now. But because it's a pooled sample, we want to be sure that we can cover this with at least 100x. And with that, thank you so much for your attention.
We should have a little time at the end for some questions. We'll let Dr. Beckman go now, and then we'll open up the floor to the two speakers.
Okay, well, thank you very much to Paragon for inviting me to be here and give this talk. It's a little different area than Ed's talk. Mine is more in the area of clinical diagnostics, and so what I'm going to be describing today is our approach to develop and automate a next-gen sequencing platform for pharmacogenetic testing. And the focus of this will be mental health and medication management. And by the way, I'm Matt Beckman, and I've also worked in academia for a large part of my career, but then I switched to the clinical diagnostics probably about a decade ago. I've never really looked back. I feel like I've really found a field that I love, and it's been a very good transition for me. So now GENETWORx was a company that I helped to co-found, and I was the very first employee that walked through the door and started up this lab. We built it in a library. And we now, 4 years into that, we're purchased by Recovery Centers of America, or RCA, and they're a leading provider of treatment for substance abuse, alcohol, fentanyl, opioids, and methamphetamines. So they have centers up and down the East Coast, and they've now kind of migrated into the Midwest. Pennsylvania, New Jersey, Maryland, Massachusetts, Illinois, and Indianapolis being the more recent one. So they have 10 in all and cover about 1,000 beds among the different centers that they have. They also have some outpatient clinics and some healthcare clinics. So buying a molecular lab was good for them in two ways. One, it was an investment, which they wanted a return on their investment. They're owned by a hedge fund company, and so they were buying a molecular lab, and the person at the time who was our CEO was someone who was really good at starting labs, and he promised to them that he would build a clinical chemistry component to us, and then they could send their toxicology samples to us and their drug screening samples to us, and then we also do some sexual, some STD testing for them as well in the molecular lab. So this is GENETWORx and what it looks like. It's located in Glen Allen, Virginia, and we're a CAP and CLIA accredited lab. And we got into the testing for COVID, and one of the machines that we have is a very high throughput PCR style machine that can do up to 768 wells. And that's something that a lot of clinical labs don't have. You might get to 384, but getting that extra notch is like a lot. So we were able to put that to use, and we've done over 12 million tests since we started testing in March of 2020. But the battle is kind of slowing down, as everybody knows. If you're in this field where you're testing for COVID and you get into the high throughput side of it, it's a very painful process to wind down out of that. I think at one point or another we had over 300 people in the lab, the clinical lab, doing the testing. It was like all hands on deck. It was like, you know, all the people coming to make flags for the war or something like that. It was a big enterprise, and our parent company, RCA, helped us to find more of a Six Sigma style approach to the workflows and reduce the errors and get automation and a lot of things in place so that we could get through transitioning to that type of testing. Something came on the screen there. Okay. All right, so I got it. GENETWORx currently is, repositioning itself in the marketplace. We've had some changeover in our leadership as well. And we're rolling out diagnostics for patients' mental and physical health, and I think that the combination of what we are as a molecular lab with the clinical component, that's full service. And then you also combine that with the interests of our parent company, and mental health becomes a really big thing. And you think about the stresses and the things that have gone on during the pandemic phase, mental health issues is something that no matter who you are, you're dealing with it in one way or another. So one of our big initiatives will be pharmacogenetic testing. We've always done pharmacogenetic testing. In fact, our company was founded on doing PGX, but on a much smaller panel kind of scale. But what we're planning to do in this regard is to apply it in a more focused way, and that's where really the clinical areas are heading. Okay, if you're working clinical testing, you know that. So what is PGX for anyone who's not into this kind of science? It's more of a precision type medicine. It's individual variants in genes that can impact a person's response to medications and also the dosages that work for them. Pharmacogenetics helps to translate an individualized improvement in clinical utility back to the population as well. So just as you saw in that last talk, there's a community effect that you can have with testing at a certain level. PGX test is designed to the individual level, but it can also be applied to the population. And that's kind of where we want to try to take it in the long run. The near run is just have a test. And then the target condition of PGX needs to be specific to the medical necessity. And I wanted to have that line in there, especially for the labs that are dealing with the regulations that are coming down with MolDX and other things. We're going to have to apply everything that we do in a molecular lab test, especially if it's an LDT, to different kinds of standards as we go into the future. At the same time, it might take several genes to cover the complexities of a specific disorder. So when you think about mental health, there's a lot of different genes that are part of that have to be encompassed into certain panels. But for reimbursement and trying to treat people, you're not going to be able to have panels that have hundreds of genes either. You're going to have it down to a certain number of genes. So the products that you're going to have are going to be more narrow. But the medication management side, it's a big problem. 16% of total healthcare spend is really wasted. And the biggest drivers are the misuse or non-use of mental health medications and lack of precision medicine. So if you can take a population, let's say a corporation that has many employees in it, you could probably get to some population health components that would really be helpful for helping that company long-term save money in their insurance outlays. But the providers do not have the time and the information to meet this demand. It's very complex. And so one of the things we have to focus on in a lab setting is how do we make that simpler for healthcare professionals who are treating the patients to use the data. What patients will benefit from PGX testing? It's clear that if you read enough of the literature on this anyway, that all patients can benefit from this kind of testing. So before prescribing, understand the risk factors for disease states. That's one area. In an acute event, understand potential cause of the event and choose the correct therapy and try to get to therapies a little sooner. and calibration of the dosage. And then in chronic care, the personalized approach to improve success in the initial therapy, and then improved management of disorders like depression, anxiety, and other things. So the goals that we brought into this from our executive team to what we're developing in the lab, we want to introduce a clinical pharmacogenomics service. That's obvious from the interests of our parent company and where we're going with a lot of the patient health care there. We want to bring this into the marketplace in 23. The product that we're developing will be developed to meet these MolDX standards and also New York State requirements for the validations, which means that there's going to have to be clinical utility and validity, and the necessity, the medical necessity, has to be homed in on. The intended use for the mental illness, or for our panel, will be the mental illness and neuropsychiatric disorders. This product will also address high-level difficulties associated with NGS, technical things, the cost. You heard a little bit about that in the last talk, that next-gen sequencing can be a very costly thing, and I'm going to give you the reasons why we partnered with Paragon Genomics. It has a little bit to play into that, as well as their support for a group like ours. And then high-level success, I'm going to want to share with you the high-level success that we've already had with the Paragon chemistry. So in terms of mental illness, not to get totally into a talk on mental illness, but it's associated with psychiatric disorders like depression and attention deficit, narcolepsy, schizophrenia, bipolar disorder, and then epilepsy, which is conventionally considered to be a neurological disorder. Many of the drugs that are used to treat epilepsy are also used to treat psychiatric disorders. And then, of course, there's substance use disorders, and a lot of these things cross over to one degree or another, but they do have their specific component as well. And then there's anxiety disorders. There's generalized anxiety, panic disorder, social anxiety disorder, and certain other phobias that can also be a part of this. And so in development of the approach, you need to think about a couple of things initially. First of all, like what scale are you going to be working on? And what do you want to do with the panel in terms of size and scale? So the extraction procedure that you choose has to be regulated in that sense. And then you have to decide on how you're going to prepare the library and how that work can be done in the setting of your laboratory. The next big part of the approach is the templating and the cleanup. Those are the steps that get highly technical. You can have some automation associated with the templating parts, and the cleanup parts have to be sorted out with how are you going to clean up and get rid of the background noise. And then, of course, the sequencing and analysis, and along with that comes bioinformatics. You have to have somebody in your group that has that bioinformatics ability. And then our equipment, we have both Illumina and Thermo Fisher, so we could have gone either direction in terms of that, but we chose to use the Thermo Fisher system for the platform, and then they already have a plugin that can help you output the data and put it into report format. So you can have genome-wide interrogation. When you get into a next-gen sequencing component, you've got a much higher scale that you can work with. It gives you different parameters you can consider. Here we're looking at 144 gene targets, and I think this is actually expanded a little bit from where we were. You can tailor design smaller panels from a more comprehensive panel too. So it consolidates the workflow that you're doing in the lab. Rather than having a whole bunch of machines that are all doing these different kind of focused panels, you can have a comprehensive panel and then have different reports for different test requests. And so we're working in that sort of manner, and that consolidates the amount of footprint that we'll have in the lab on that. And then you can get about 40 to 80 tests per chip in this kind of thing, and the cost becomes a big factor. The more you can put on a chip, obviously, the lower your costs are going to be because those chips are very expensive. But you want to get the target cost per test somewhere in that neighborhood of 150 per test. And that's not including all your overhead costs and things like that. So it has to be adaptable also to automation for greater precision and specificity. I worked in a lab for well over a year where we did the preparations of the libraries with AmpliSeq every single day. And if you're trying to describe to somebody that this is something you should do in today's times, it's probably not something they're going to want to do. So it's very technical, it's very labor intensive, there's a lot of hand movement and stuff like that. So if you can automate that, that's another part that you want to focus on. And then scalability is another consideration that you have to have. And you can have more machines, but you also can have scalability with the Thermo platform with the different chips, because it's the same size chip physically, but you have more wells in the higher scale chips. So, and the cost plays into that a little bit, but if you're doing more patient samples, you erase some of that. Okay, Paragon. And what we found by first our own research on this and then calling up Bruce and the other people from the group and talking more about what can you guys do with us on this kind of a problem. Our goals in this conversation were to have a scalable panel. It has to be sensitive for assay development, for a clinical test. Have a uniform amplification so that patient to patient to patient, you're going to get similar results as long as you're dealing with it the right way with the input. Low background was a key thing, and having a slick workflow. And what I mean by this is if you're doing the conventional AmpliSeq methodology, you're going to spend 8 to 9 hours just doing a library prep. If you can do this in a much shorter period of time, you can extract the same day that you're running your library prep. And then you can template overnight and load your chip and sequence the next day. So it becomes a test that's kind of like within a time frame that a patient wants, even though pharmacogenetics isn't necessarily something you need the next day. Some of the other features that we discussed with Paragon was to have a way to do some fragment analysis, go to more unique genes that were not in our current PCR panel, and then get higher coverage of certain NGS targets. And then you also have a copy number associated with like the CYP2D6 gene. So all of these things are things we wanted to try to build into our panel. And let's see here. I don't know if I just went too far. Here we go. All right, so in the optimization part, and I'd say right now our test is in the phase where we're doing the qualification to get to what we want to validate. And we're very, very close at this stage. But you can see from this that you got fragments. Okay. Sorry. Here we go. Fragments that are in a particular size range that it's very uniform, and then when you take a standard, you can see that it can give you very consistent data for the fragment size. And then I know that this is probably a little difficult to see, but we can generate very good coverage using this library scheme. And then the read lengths are also very uniform on the system. And then this just gives some of the parameters for the templating quality, and for the most part, it's reaching levels that are very, very reproducible and strong quality. And then alignment with the actual reference-based sequences is also very strong. So in summary, we've taken this kind of novel approach of taking the traditional methodologies and combining them with what we've been able to do with Paragon and create, a system that we can automate and we can scale and we can do what we need to do with it to get to the numbers of patients that might be achievable in, like, say, a larger group or population, as well as individualized enough for the patient. And then applying automation will make this for greater precision and workflow throughput, and the platform scalability and expansion to serve some of these, genetic components that we want to do. So in all, the panel has about 50 genes, 200 SNPs, and then we cover with drug-drug interactions and drug-gene interactions in the analysis and the reporting. And then the acknowledgements here are, first of all, the R&D division that I work with. So my senior scientist, Tyler Northcutt, and our bioinformatics scientist, Chris Oldfield, and our manager of the molecular lab, Carl Chile. And then we also have a set of pharmacists that have helped also with this. So thank you very much.
We'd like to invite any questions you have for either of our speakers today. If you guys want to come up too, that'd be great. Jason here will bring the microphone to anyone that would like to ask any questions regarding either of the two talks today.
Thanks a lot. I had a question for Ed. Very good talk. I was just wondering what kind of challenges you had with sample prep from wastewater, and how were you able to address those? Thank you.
Yeah, I can't, sorry.
I think that was a big key for us. Being able to find reagents that in some ways defied the original expectations of what SARS-CoV-2 should look like when you use a centricon to optimize for a virus that's a certain size in a clinical sample versus a wastewater sample. So a lot of the assumptions in the beginning were that the genome was going to look very similar from clinical samples and wastewater samples. That was very, very wrong. And so we ended up using a number of different reagents and kits. And finally, we chanced upon a kit that worked really well for us that we then tested on all of these different library prep kits. And I don't know what the magic is, but with Paragon, we consistently got good coverage across the genome and high depth, number one. And number two, the cost per sample, when we compared that with another good collaborator of ours, Illumina, it was just night and day. So we're not running tens of thousands of samples, but we're running hundreds or low thousands of samples. So that just made more sense for us. But the key step for wastewater surveillance is extracting high quality nucleic acids before transitioning on. Yeah.
I have an additional question, really just technical. I assume the wastewater is quite diluted. So do you actually concentrate it before you run it? And the second part is, I couldn't see it on your slide, but it was very interesting. What is the final concentration that you get, which you can see compared to?
The final concentration of the library or of the?
Of the organism that you found.
When we extract RNA and or DNA from wastewater, the microorganisms that will always be at the highest amount of concentration will be E. coli, bacteria. And so looking for monkeypox, influenza, RSV, chlamydia, that's only going to be a real small fraction, 0.001%. And so when we get a concentration of RNA or DNA at the end of the extraction, we have no idea. And so we can run a qPCR to guesstimate how much is there with a standard, and then go from there. But we don't do it that way for all of the samples for SARS-CoV-2, just because it's an additional step that slows down our processing. We want to go from sample to answer to public health surveillance within 3 or 4 days with variants.
You did show a nice increase. I must have correlated with some sort of number.
Right, so that's a qPCR result. So at the end, we can match that up for SARS-CoV-2, but more recently with looking for other pathogens, and then running 100 libraries. We don't do that for every sample. But typically when we run qPCR, we're looking at CT values of around 30, mid-30s.
Dr. O, another question?
You're back.
Oh, okay.
SARS and influenza are both RNA. I
Mhm.
do a lot of research on HPV,
Mhm.
DNA. So how do you think the RNA did not get so degraded and all that went through toilets to pipes to whatever?
Yeah.
Usually, messenger RNA you want to store and freeze it right away, and then, but this thing survives, intact,
Yep.
so to speak.
Yeah, absolutely, right? That was the biggest hurdle initially when we went in. We asked ourselves, does this even make sense to do this? We can barely keep RNA from human tissue stable in the lab, let alone now go out to a wastewater treatment plant, have that sewage go from our homes all the way out multiple miles and then still extract it, and sometimes even leave that wastewater in a fridge for 3-4 weeks, and yet we still can do that, suggesting that it's not free RNA that's floating in that wastewater, that it's encapsulated. It's still potentially within an intact virion, but we don't have the exact answers just yet. Running EM on that material has been a little hard.
Also, I lived in Las Vegas before. So how did you pick, or how did public health pick where to go get the sewage location? I mean, technically, if you had a college, then everything's funneling through, maybe go get some samples morning and night. But how did you get it from the entire city of Las Vegas? I mean, that's insane.
Similar to Arizona, California, a number of zip codes all feed into a wastewater treatment plant. So each of these wastewater treatment plants can collect from a collection of zip codes. So we knew from the get-go where to go if we wanted to get representation from Henderson or from Summerlin or from City of North Las Vegas. But what we wanted to do was do better, and we wanted to go closer to communities. So we had to work with the city to understand the sewer lines. And so that was the academic part of it. And having a lot of undergrads to go out, pop manhole covers. And yes, it was a new science for us.
Get Mike Rowe on.
This question is for Dr. Beckman. You mentioned medication management as part of your PHARMACOGENETICS program. Could you describe the steps or the things that you're doing for doing that portion of it?
Well, the medication management is, yeah, thanks for that question. Medication management has been pretty much the focus of the work to this point with PGX, but I don't think that it achieves the bar for alone for medical necessity without a focus on a particular disorder. So the medication management that we've done traditionally up to this point, which probably at this stage would not even be approved by a Palmetto, for instance, has been P450s like 2D6, 3A4, 3A5, C19, C9, VCOR, There's about 9 or so genes that are really key in that, and if you look at CAP surveys, they include those particular genes, all the way through. But that's got to be part of what we have, right? It has to be part of the panel that you're offering in order to get, because certain genes like 2D6 and C19 are going to be the more reimbursable genes. But in order to get at a particular focus, you're going to have to show the clinical utility, and clinical validity. So it's going to have to be a combination of it. I didn't want to focus too much on the medication management because it's kind of the thing that we're kind of running away from, in a sense, so that we can get to a more focused thing that will be approved.
It's definitely the more tricky part, which is
Yeah, but we have pharmacists that help do the report sign out, and then when people have questions, they call back in. Pharmacists are available in our group, so that's how we've dealt with that.
Thank you.
Mhm.
I have a quick question.
I was just wondering about the patients that go to the addiction clinics. Do they all get preemptively tested, once they get into the clinic? Or how do you select the patients?
Yeah, that's a really good question too. So we've reached out to the medical directors of the centers to see if they would like to be part of a pilot study. So we can look at population health in some of these communities. It's a total big ethical thing to them. From their side, being directors of people that have mental health disorders and things, that's a big area that they guard as best they can. So we're sorting through a lot of questions, more questions than I ever thought we'd ever have to kind of deal with. But I think it's worth getting to the solutions of that and then seeing what we can do with it, with those pilot studies. And then that would be a way to or expand that kind of concept, to a bigger part of the population.
I have a question related to what you were talking about, partnering with employers and insurance companies to help improve outcomes there.
Mm-hmm.
Specifically, who winds up owning that information? Is it the patient? Is it the employer, the insurance company?
Yeah, that's another really good question. Those are the kinds of factors that we're dealing with right now. And I don't know that we have specific answers to that yet. There's going to have to be a lot of discussion to get to where that lies. There's a lot of lawyers involved. That's usually where my scientific brain kind of shuts off. It's sort of like when I talk about fantasy football in front of my wife. Can't keep her attention.
So now we just actually have another question for Ed. I might have missed it, maybe, but what is then the final volume that you put into your DNA extraction? Is it being enriched prior to the extraction, or?
Yeah, so here's the real surprising thing to us. People were talking about liters of wastewater. We ended up using 10 mils, 40 mils to get representation of about 1 million people.
And that is going directly into DNA extraction.
That's right. 10 mils, 10 to 40 mils going into DNA extraction and using that to generate a library, using a fraction of that to generate a library. Let's say about 50% of that to generate a library. Yeah.
Thank you, everybody, for coming. Really appreciate it. Thank you for our guests for attending. Have a wonderful rest of your day.